Hi everyone. I haven't looked at the zeroth law and first law of thermodynamics in our previous class. We'll be reinforcing this knowledge and this understanding by going through a couple of examples. But before we do, I'd like to draw our attention to a correction in the previous in the slides provided online on Blackboard. Please take note. In the slide, it had previously shown sign convention for it and for work done, but take note of the correction here. So it's for heat, it's positive when transfer from surroundings to system. That means heat is being gained by the system. So when heat is being gained by the system, positive. When heat is being lost by the system, so when there is a transfer from system to surroundings, that is negative. Take note for work done. So what we have for work done is different from what you have for heat. So for work done, what happens is when work is done by the system, it is positive. When it is done on the system, it is negative. So take note of those two differences. It will become clearer when we walk through the examples in the next couple of slides. So our example 1 says a system consisting some fluid is in a stirred tank reactor. The rate of work done on the system. So take note of this. Work done is on the system. On the system by the stirrer is this. That's it. Work is in watts. The heat generated due to stirring is dissipated, so that means heat is lost, so that's negative. So take note of this. Work done and so work done on the system, remember we said is negative, and whenever heat is lost is negative as well. So take note of those. If the heat transfer to the surroundings is this, so that means the heat being lost to the surroundings is that. Determine the change in internal energy. So we've been given from the first law of thermodynamics that change, in the previous class we saw that change in U equals Q minus W. Remember Q is Q that talks to the heat, and then W that is work done. And remember, we've said since the work done is on the system, whatever we have will be negative for this, and this also will be negative, the heat, since it's been dissipated. So, and also another thing you need to remember, so this is the first thing. We've got the equation. We said remember those the conventions. So the next thing we need to take note is consistency of units. So let's start with that. So for the work done, W, which is 1677.825 watts, is the same thing as 1677.825 joules per second. So take note of that, consistency of unit. And then for the Q, so we want to ensure that Q and W have the same unit. So for that, we'll say 3,400 kilojoules per hour. So we want to convert that to joules per second. So that will be 3,400 times 10 raised to power 3. That converts kilojoules to joules. And then we want to convert hour to seconds. That will be divided by 3,600. So if you do that, we should have this should give us 944.44 joules per second. So looking at this, we have Q and W in the same unit. Q and W in the same unit. So now let's plug these two into the formula we've been given. So it simply means change in U equals, remember our Q will be negative, minus 944.444 minus minus 1 minus, remember this minus, that's the one what we've got in the formula, but we've also said since work is being done on the system, it will be negative, so we say minus 1677.825. so obviously minus times minus becomes plus. So if you so minus, yeah, so minus minus becomes plus, and if you do that, we should be left with minus, let's just punch that into our calculator, and when we do that, we should have 733.381 joules per second. So take note of that. So but remember, the answer, the question is so we are looking at determine the change in internal energy. So we can say like this, and we can also interpret it to say the internal energy of the system increases by 733.381 joules in 1 second. So this is the way to interpret this answer, that to say that the internal energy of the system increases by 733.381 joules in 1 second. So that is that. So let's look at another example, 3.2. A system consisting of a gas confined. So every detail provided is important. The gas is confined in a cylinder, is undergoing the following series of processes. So a number of processes is taking place before it is brought back to the initial condition. So the first process, a constant pressure, that by now we know about isobaric process. The second part, a constant volume. We also know that isochoric happening with, we know constant volume. And then we have an adiabatic process. All right. So in order for us to understand this better, let's put it in a diagram. So the PV relationship, remember we did that in a couple of classes ago, PV relationship. So if you have a pressure and then we have a volume. So on this axis, we have a volume. On the other axis, we have our pressure. So so the first process, which is 1 to 2, a constant pressure process, when it receives 50 joule of work and gives up 25. So work being done there, it shows that the so at that point the we are seeing, remember that is at constant pressure, so it's the volume that is changing. So 1 to 2, at 1 to 2 we have that happening in this direction, volume changing, but the pressure is the same. Remember that there is no change in pressure. The only difference is in the volume. And then 2 to 3, a constant volume. So constant pressure, 2 to 3, constant volume. So if it's constant volume, so let's say we have a point here. So we have a point here in volume. So it's constant, but the pressure is changing. So 2 to 3. And then we have a third process, an adiabatic process. So that would be 3 to 1. So we have an adiabatic process, which we can draw that way with a bend. So take note, for the adiabatic process, note heat exchange between system and surroundings. There's no heat exchange between the system and the surrounding. So let's move on. Please take note of the different values we've been given. So 50 joules of work gives, we've seen. So we know the value of the work done. We know the value of heat, Q. So we have all those values. So the question is determine the change in internal energy. So we are looking for change in U during each step. So we need to look for change in U here. So let's call this change in U1. For each step, change in U2. For the third step, change in U3. So determine the change. So what we're looking for are these values during each step, and the work done during the adiabatic process. So we're also looking for the Q, let's call it Q3. 3. So those are the things we are looking for. So, but let's start with what we've been given. We know our formula, which is change in U for the first law of thermodynamics equals Q minus W. Q minus W. So I haven't been given that. So for step one, so for step 1 to 2, which is at constant, all those details are important, constant pressure. So what happens there? We said that it receives work. So work is being done on the system. So hence, the value of work we've been given will be negative. Hence, negative. So you remember I've been given value of 50. So our value minus 50 joules. So take note of that. And then it also says it gives up heat. Gives up heat. What does that tell us? Hence also it will be negative at Q. So W here, Q there. So we have those values, negative minus 25 joules. Everything, both are in same units. So using our change in U formula, we know change in U. So the first change in U will be equal to minus 25 minus, remember that minus in between this minus there, and then minus 50. If you do that, it gives us 25 joules. So that is for the first step. Let's move on to the second step. Step 2 to 3, which is at constant volume. So what happens here? Let's see what's happening here as well. We know we'll still be using this same formula, but remember, for work done, what happens? Remember from previous class, we've seen that work done equals pressure change in V. So if there is no change in volume, since there is no change in V, it simply means there is no work done. Hence, we say change in U 2 equals Q, since our W equals 0. So so in this case, we just say equals 70. So we've got the Q, and remember let's go back to the question. A constant volume when it receives. So for the heat, it receives at this point. So if it's receiving heat, what is that? Positive Q. So that makes it 75 joules. So we've got that value, 75 joules. Let's move on to the third stage. So the third stage, step 3 to 1. So at this third stage, since it's adiabatic, remember, so since it's adiabatic, as we discussed in class the other time, if it's adiabatic, there is no heat exchange. So if there is no heat exchange between the surroundings and the system, so in that case, our Q will be equal to 0. So if Q is equal to 0, change in U3 then is equal to minus W. Remember from our formula here, this formula, that's what we're still working with. So if Q is 0, that means change in U3 becomes minus W. So remember, our question is, we're looking for this. We've gotten it now. We're looking for that. We've gotten it now. We're looking for change in U3, and then we're also looking for Q3. So let's move on to solve the rest. Take note that this system, as we showed in this picture, it's a cyclic system. It's a system in a the system is a confined is in a confined cylinder. Let me put it that way. It's confined in a cylinder as we have it here. It's a cyclic system, and in a cyclic system, change everything that is happening, change in U1 plus change in U2 plus change in U3, everything equals to 0. You remember, as we've learned with thermodynamics, you can transfer energy, but you don't it can transfer energy, you can transform energy, but you cannot create or destroy. So hence from this we can say change in U3 equals, so if you leave a change in U3 here, you make it subject of the formula, it becomes change in U1 minus change in U2. So if we plug in our values, minus 25 minus 75 equals minus 100 joules. Minus 100 joules. So that is the work done. So that is the work done for in the adiabatic system. Hence, yeah, okay, so that is the work done in the adiabatic system. So remember, we can this is changing U3, but remember this formula. So if you take that back there, so it simply means minus 100 joules equals minus W. So that shows us, so our work done under the adiabatic system is 100 joules. So what we can say is, hence the work done during the adiabatic process is 100 joules. 100 joules. So let's move on to a third another example. It says calculate change in U, internal energy, and change in H. So internal energy, change in internal energy, internal energy, and change in H, which is enthalpy. For 1 kilogram of water, when it is vaporized at the constant temperature of this, so we've got a temperature, and the constant pressure, we've got a pressure. So let's write down what we've got. T 100 degrees C, and we know T for water at 100 degrees C, we know that is the boiling point. And at the boiling point, what is happening? You're having your liquid being converted to steam, which is gas. What this also infers is you are having expansion. You remember the volume of your liquid is lower than the volume of your gas. So remember, we've seen an example in one of the previous classes that when you have expansion, the work done is positive. The work done is positive when you have expansion. So take note of that. The specific volumes of liquid water and water vapor. So water vapor is steam, liquid water, we have this, so we have the values there. For this change, heat in the amount of that is added to the water. So if it's added, we know our Q is positive. That should be, you can say that should be obvious since you are boiling the water. So let's just plug into our let's plug in what we've got into our equations. Remember, W, work done, is P change in V. So if we plug that in, we've got our pressure, which is 101.3. Always remember that it is essential to have consistency in values. So we want to ensure, so remember it's kilopascal. So times 10 raised to power 3 multiplied by the change in volume. So change in volume from the higher volume, which is that of the gas or the steam, 1.673 minus the liquid, 0.00104. So we've got that, and that should give us 169.37 kilojoules. That is the work done. So let's calculate the that is the work done. And remember, it's positive since heat is added. We've mentioned that earlier on. So in that case, from what we've got, we know change in U equals Q minus W. which is 225. Remember, we've also said the heat is being added is positive 2256.9. We are given that, and then and remember 2256.9 is in kilojoules. Remember that, and what we've just calculated is in kilojoules. So we have those 2256.9 minus 169.37. That should give us 2087.53 kilojoules. So remember, that's a change in internal energy, but we still need the change in enthalpy. So we've been given we know the formula: change in U plus change in PV. Change in PV. Take note of that. Unlike with W, where in W is P, change in V. So the emphasis is on change in volume when it's work done, but when it's enthalpy, it is changing both pressure and volume. So take note of that, and remember, in this case we've been given it's at constant pressure. So if it's at constant pressure, this formula then becomes change in U. So change in U plus, so remember this would have become change in U plus change in P plus change in so would have been, change would have been change P and that. But remember, since P is constant, so what happens is this will, since that P is constant, or right, it would have been that. But since that it would have been change in P, change in V rather, change in P, change in V, not plus, change in P, change in V. But since our P is constant, so it becomes P change in V. P change in V. So let's plug in what we've got: 2087.53 plus 169.37. P change in V. Remember, P change in V. Remember this? We did that earlier on for, so P change in V. We remember we did here for work done earlier on. So if you plug that in, you should have this. So P change in V, we've gotten that. We just plug that in: 2256.9 kilojoules. 2256, or we can rewrite it as 22.26 times 10 raised to the power 3 kilojoules. Thank you and all the best. If you've got any questions, please don't hesitate to send me an email. You can also send me a message on WhatsApp, so that if there is any need for clarification, I can get that sorted. All the best.